You ever like sitting around eating a hamburger, not really paying attention to what you're doing, and suddenly you go back for another bite of that hamburger and it's gone? Gone. Did you ever notice that? How terribly depressing that feeling is? Yeah, nature's like that too. Nature doesn't want things to change. You know, if your grandma's all fine and dandy and then suddenly she's gone, you regret that. You miss her because you don't want change to happen. Nature also hates change. You want everything to stay as it is, and so does nature. So, see, the thing is, the only other thing you need to know about Lenz's law, here's Lenz's law. Lenz's law is that minus sign right there. This minus sign is Lenz's law. And what you need to know is that nature hates change, and nature is counting the amount of flux that goes through every loop in the universe. So right now, this ring right here, this ring, nature's keeping track of how much flux is going through that ring. And if I change the flux, then the ring is going to try not to allow the flux to change. Let me try to state Lenz's law in a concrete way. Okay, all loops, I don't care if they're made of metal or of like a ring of my flesh, I don't even care. All loops want to keep the flux through them I'll say themselves. All loops want to keep, ooh, look, I found elves. What fun. All loops want to keep the flux through themselves constant. And they will do whatever they can to keep keep the flux through themselves constant. And you already know that if I make a current going through this wire, then that current will create a magnetic field, right? So if I make a current this direction, then the magnetic field will be into the page, and if I make the current that direction, then the magnetic field will be out of the page. You want a secret right-hand rule for that? Watch this. If I do this, that's a loop, and now I need to put my fingers in the direction of the current, and my thumb will show the direction of the field on the inside. Watch this. Whew, like that. Did you see that? But if I turn it around, then I put my fingers in the direction of the current, and my thumb will show the direction of the magnetic field in the middle, like this. Whew, like that. Try it. Try it. But you got to try it really fast because I don't have a lot of time for that. That's a secret rule. Watch this. If I have a current, let's say it's going, let's say it's just a loop. Just a loop of metal this direction. And if I bring a magnet over to it, then I'm getting more and more field going to the left inside of my loop. Do you see that? You agree with that? The field is becoming stronger and stronger and stronger, pointing to the left in my loop. And my loop doesn't like that. So my loop will create a field that points to the right. My loop creates, as I get closer and closer, my loop hates the fact that you're changing the field through it, and so it will create a field to the right. And the only way that it can create a field to the right is, check that out, it has to make a field it has to make a current going this direction. This up through here, like that. You see that? So it has to make a field that opposes the change in field from the approaching magnet. What about, okay. What if I have the south side and it comes over here and approaches? Then I'm getting more and more field pointing to the right on the inside. Field's pointing to the right on the inside, and the loop doesn't like that. So the loop will try to make a field that points to the left, like that. And so, in order to do that, it will have to have a current rather, going this direction. The other way. Interesting. Or I could take the north pole of this magnet and bring it further away. Do you think this loop likes that? No, it hates every single change that you make. Nature is really, really finicky. You pull that sucker away, then the field inside of here is getting weaker, pointing to the left. So it's getting less and less field to the left, but it misses that hamburger that it was eating. It misses that field that was pointing to the left. So it will make a current to get more field pointing to the left, and that means the current will be this direction. Like that, if I'm removing the north side. And similarly, if I'm removing the south side, it'll kind of be the opposite of all of that. So let's go through a couple more examples of Lenz's law. If I have a field that is uniform and into the page down here, but there's no field up here, and I've got this loop, and the loop falls, there will be a current induced in the loop as the loop enters this field. Which way will that current be induced? Well, let's talk our way through it. The loop will see that the flux through it is increasing into the page. So the loop thinks, that's not good. I want no field to increase into the page. So it makes a field out. And the way to make a field out is current goes which way? Figured out. Current counterclockwise. Check it. So the current will be this way as the loop is entering that field. Now, you're kind of wondering how long it will take nature to get used to it, because I could give you a corollary question. I could say, what if that field doesn't last forever? And now I've got, watch as I do this, this is going to be kind of sneaky here. I'm going to put a dotted line here and say that the field is ending here. And here my loop is still falling. My loop is still falling. It fell into the field and got a current going to the, oh my goodness, if this current stays forever, then the loop will never have a changing flux inside of it. But check this out, if it got used to it, I don't know what that would take, but let's say that it got used to this new flux. Now it likes the new flux. You see how fickle nature is? Nature's like, oh, I really want the old flux. No, wait, it's okay. I'll get used to it. And now it can't stand the old flux because it wants to have the new old flux. Sorry, that's not very clear. If there's a magnetic field here and there's no current going through the loop, then the loop likes the present magnetic field that is going through it. So as the loop falls, the velocity is this direction. You can do this in terms of forces on charges, etc. But we can also use Lenz's law, and that's a lot cleaner. As the loop is exiting the, I'm going to offset it just a little bit so you can see that. As the loop is exiting the field, then I find that the loop wants to remind itself of that pleasant field that was into it. And it will create a current. Okay, so let's make some notes here. We've got decreasing. We've got decreasing field in, and the loop says sad, doesn't want to have decreasing field in, and so it makes field in. Ooh. And the way to do that is to make a current which way? Clockwise. Cool. So there will be a clockwise current in this case as the loop is exiting the field. Notice that here we had a counterclockwise current as the loop was entering the field, and we'll have a clockwise current as the loop is exiting the field. Now that's presumed, oh man, you got to figure out what this is. What could make what makes loops get used to the field they're in? So that's your trick. Your challenge is, what the heck can make them get used to the field that they're experiencing so that the current is gone and they suddenly like what they've got. But there's one more thing. I hope that you have seen a fantastic movie. These loops remember how much flux is going through them, and so in a sense, they are storing flux. Storing flux. Are you where I am right now? Storing flux implies flux capacitor. So you've got a flux capacitor. I wear a flux capacitor. Every ring is a flux capacitor. Ever notice that? How terribly depressing that feeling is? Yeah, nature's like that too. Nature doesn't want things to change. You know, if your grandma's all fine and dandy and then suddenly she's gone, you regret that. You miss her because you don't want change to happen. Nature also hates change. You want everything to stay as it is, and so does nature. So, see, the thing is, the only other thing you need to know about Lenz's law, here's Lenz's law. Lenz's law is that minus sign right there. This minus sign is Lenz's law. You ever like sitting around eating a hamburger, not really paying attention to what you're doing, and suddenly you go back for another bite of that hamburger and it's gone? Gone. Did you ever? And what you need to know is that nature hates change, and nature is counting the amount of flux that goes through every loop in the universe. So